Let's start by breaking down how normal attention works and seeing what the downsides are when we actually get to the matrix by matrix multiplications. Okay, so let's say we're inside a head, and let's say the sequence length of this transformer, to make it easy, is going to be 16. And let's say the dimension of this head is going to be 2. Okay, so now we have our hydrated Q, K, and V values, the query, key, and value matrices, and we want an output. So let's first describe how attention works, right? So we take the query matrix, multiply it by the K matrix transposed, right? We divide this by the square root of D, and then we do a causal mask over it if we're doing causal tension. And then we take the softmax of this. And then finally, after all of that, we multiply by V, and this equals O. So now I want to break down how this matrix multiplication works. Okay, so let's start with Q, which is going to be a 16 by 2 matrix, right? 16 sequence length by head dimension. K, which is the exact same dimensions. Okay, V, which again is the exact same in dimensions. Okay, so let's first do Q transposed K. Q times transposed K. So this is 16 by 2 transposed by K, which is 16 by 2. Okay, now how large is the resulting matrix? The resulting matrix is going to be 16 by 16, right? Here. Now, this is fine because the sequence length of the transformer is only 16. But imagine that the sequence length instead is 100K or 1 million, like Gemini's models, or even 10 million, like Llama's models. This means that we have to materialize a sequence by sequence length matrix just to get the attention scores. This will cause GPUs to go out of memory quite quickly. And generally, memory is very scarce, and we want to make sure that we are being as memory efficient as possible. So if there's a way to do this without having to materialize this sequence by sequence length matrix, we should do it. Let's finalize this though. So we have our 16 by 16. This is multiplied ultimately by V, which is a 16 by 2. And we're left with the output, which is going to be a 16 by 2. Because a 16 by 16 uh, matrix multiplied by 16 by 2, you're going to get a 16 by 2. And this is going to be the output. Okay, so this is normal tension. This is all fine. It's well and good. It'll get you the right answer. But again, we have this massive matrix materialization. So now let's see how we can improve this. So we still have our same Q, K, and V's, but we're going to add a new variable to the mix. It's going to be called a block size. So sequence length is still going to be 16. Head dimension is still going to be 2. But now we're going to add a new value called the block size. And this is going to, let's just say, be 4. Now, what does this mean? Well, the idea is, let's start with the output, right? We know what we want is a 16 by 2 output, right? So is there a way that we can, instead of materializing the entire sequence by sequence matrix for attention, if we could possibly split the output, or really the Q, K, and V matrices into blocks, and then accumulate over many smaller matrix multiplications the final output? So it turns out that there is a way to do this. And so let's walk through this now. So you have your normal Q, K, and V. And remember, these were 16 by 2. So let's draw this 16 by 2, 16 by 2, 16 by 2. Okay, but now we're going to split up the sequence. Instead of 16, we're going to split it up into blocks with a size, a height of 4. So 16 over 4 is 4, so that means we're going to split this up into 4 pieces. 1, 2, 3. And let's call this output 1, output 2, output 3, output 4. Let's split 1, 2, 3, 1, 2, 3, 1, 2, 3, Q1, Q2, Q3, Q4, K1, K2, K3, K4, V1, V2, V3, V4. Okay, so now these chunks are 4 by 2, right? Each one of these chunks is going to be a 4 by 2 matrix. So now the question is, now that we have these chunks, is it possible that we can do matrix multiplication on these smaller chunks, piecewise, have them accumulate into these blocks in output? And the answer is yes. So let me demonstrate how we can do this. So instead of taking the full Q, K, and V, let's just start with chunks. So let's take Q1 times K1 transposed. We're going to divide this by the square root of the dimension. Okay, now we're going to add a causal mask. Okay, now we're going to take the softmax. Okay, and now finally we're going to matrix multiply this by V. All right, so now what we've done is we have an output, which is a 4 by 2. And I'm going to walk through the matrix multiplication in a second, but this is now 4 by 2. Now, if you think about it, so we did Q1, Q2, sorry, Q1, K1, V1. But this is not the full picture because in order to get the final O1, when you multiply the whole matrix, Q1, this top part sees K2, K3, K4, sees V2, V3, V4. So we need to incorporate these as well. So really, so you have, let's call this output 1 using Q1, using K1, and using V1, plus, so we're going to accumulate, plus Q1. So we stay on Q1, but now we transpose it with K2 divided by the square root of D, masked, softmax, all of this, and this should actually be, sorry, V1, matrix multiplied by V2. And now this is going to be the output 1 Q1 K2 V2. Now we can do this exact same thing to get output 1 Q1 K3 V3, and then finally output 1 Q1 K4 V4. Let's add these up, accumulate them, and now we finally have equals O1. Now we just have to put that there. Okay, now let's just walk through quickly how the matrix multiplications work, just to get the size of everything. Okay, so let's take uh, this first, uh, this first multiplication. Okay, so we have Q1, which is a 4 by 2, 4 by 2, transposed times a transposed K1, which is going to be a 2 by 4. The result of this is going to be a 4 by 4 matrix. So now what we've done, instead of having to materialize sequence length by sequence length, we just need to materialize the block size by block size. So now this is why this approach is called tiling as well, right? Because we now can do a bunch of smaller materialized matrices instead of one larger one. And so this fits nicely in GPU memory. Okay, and now once we have these transposed, the next step, let's take this, the next step would be to multiply by V in terms of the shaping of everything. V1, which is, so this would be a 4 by 4 by, and V1 is, remember, 4 by 2, the result of which is going to be a 4 by 2, and this is going to be that output 1 Q 1 V K 1 V1. This 2 by 4, the 4 by 2. Now we just accumulate all of these, which means add them together. And now we fill in O1, and then we do the same thing for O2, which means the outer loop is running on Q2. Then do uh, O2, Q2, K1, V1, O2, Q2, K2, V2, O2, Q2, K3, V3, and so on until the entire O is filled out. And so as you can see, we're saving a ton of memory, even though we do have to do this tiling approach. So now we see how the accumulation occurs. And I'm going to get into the code, which is going to be clean and will show the nuts and bolts of how all this works. But if you can see, there's one glaring issue with the current implementation, which is this softmax here. So the softmax turns numbers into probabilities, right? It squishes numbers into values between 0 and 1, where in this case, each row needs to add up to 1. Now, the problem is this is a local softmax, right? So we're adding the softmax of Q1 times K1 transpose plus the softmax of Q1 K2 transpose. But the problem is um, these are local softmaxes, but we need it to be a global softmax. And what this means is that the softmax is uh, is correlated to these values, but when you add them, they're correlated to the wrong thing. They're correlated to different things. And so there's a mismatch. And so what we want is a global softmax, not a local softmax. So the question is, how can we fix this? Well, let's first break apart softmax and remember what it is. So it's e to the xi minus the max x over the sum of all e to the x j minus max x. So one thing we can actually do is we can keep track of what the maximum value is, which is kind of like the calibration for each round of this accumulation. And then we can calibrate the current accumulation, taking into account the new max. So let me show you what I'm talking about. So let's say we take the max after this step, right? And the max again is going to be a 4 by 1 matrix. 4 because the block size is 4, right? So there's 4 rows. So there's a max in each row. And so we go through the first iteration, right? The first accumulation, all is good. Now we go to the second accumulation, and let's say we hit a new max, which means that this soft max is going to be not correlated with this. It's going to be uncalibrated. So let's say we find a new max in the second one. Well, what we do is we take E and then we do old max minus new max. And this is now our calibration factor. That's correction factor. And we're going to multiply the existing accumulation by this factor to resize it to adjust for the fact that there was a new max that is in this somewhere. And that's actually all we need to do. And you think of what actually happens when you do e to the old max minus new max. And again, the new max is the maximum of this, um, also accounting for the old max, right? So if this second accumulation step did not yield a maximum value, these values are the same, in which case this would be 0, and e to the 0 is 1, which means correction factor is 1, which makes sense, right? It means we don't do anything. I'm going to show you how this works with code, which is going to make it a lot cleaner. But I just wanted to give a high level intuition before we dig into the code. Okay, now let's briefly check out the code for flash attention with NumPy. Okay, so let's first start with standard attention. Again, we're going to have sequence length, dimension of the head, 16 by 2. So this is what we already know what to do. Scores are equal to the matrix multiplication of the Q times the K transposed divided by the square root of the n dimension. This is for causal tension. This is a causal mask. Then we enter the softmax, right? Which is you find the max and you take the exponential of the scores minus the max, and then you do the exponential scores over the sum of all of the exponential scores. That is the softmax. And then finally, you end by matrix multiplying the attention weights by the V. Okay, pretty standard. Now, let's move on to how flash attention works. So again, we're going to do sequence length of 16, head dimension of 2, block size of 4. Okay, so here is our going to be our final output, which is going to be a 16 by 2, right? This is the final thing that we're going to return. This is calculating how many blocks to split Q up into. And remember, because the block size is 4, 16 over 4 is 4. So this is going to be 4. So this is, for Q1, for Q2, for Q3, for Q4. So um, that's what the Q start is, basically chunking Q properly. Okay, Q block. So now this is, let's say, Q1, right? Here's the running max we talked about. So we're going to initialize the running max as negative infinity. And then we also have a running sum, and we'll see why this is important. And then here's our output accumulator. So this is going to be the accumulator for O1. Okay, and we initialize it with zeros. Now, just like we chunked up the Q, we're going to chunk up the KB. And this is just the code to do that. And here's a little trick, but we can ignore this for now, which means we don't have to do some computation for certain causal indices. Okay, so here we are. We have our K block now, and we have our Q block. Now we calculate our scores, right? We take our Q block, which again is the outer loop, times K block. So this would be Q, let's say Q1, matrix multiplied by the transpose of K1 over the square root of the dimension head, mask it. Okay, now we find the maximum for this block. And so here's the new max. The new max is now the maximum of the previous max and the maximum block. Here's where we do our correction factor. So this is basically going to be the number by which we multiply our accumulation so far to recalibrate. Again, if there's no change in the max, this is just going to be 1, and then there's going to be no change. And here we are. So this is the output accumulator. Remember, this is basically the O1. And of course, for each Q, this changes. So we update our accumulator with the correction factor. We also update our running sum with the correction factor. The running sum is going to be important because the final output O that we add is actually going to be the output accumulator over the running sum. Now we have the scores. So we now run the softmax, classic softmax. And then finally, we accumulate with the exponential scores matrix multiplied by the V block. So as you can see, there's two loops. There's the Q loop, and then there's the inner loop, which for every Q goes through every K and V. And this is it. This is the basics, the intuition behind flash attention.